Math 287, Quest to College. I'm Joe Vasta. This is our last review number 5. This will help us with the exam, get us ready for the exam. So let's go do some problems. I believe it was the review for exam 4 where we did this problem here. So this problem might look familiar, and it is a differential equation which we solved using annihilators, and we solved using the variation of parameters. It was initial values here, initial conditions right here, and we got an answer. Well, now let's go ahead and do this differential equation using the Laplace transform, and then we'll turn it into a linear system and then do the problem using that. And so by doing both of these techniques, this is good because this helps us review Chapter 10, and this helps us review Chapter 9. Let's see if we can do these problems. So we're going to use the Laplace transform. I'm going to Laplace both sides. So Laplace of the left-hand side equals Laplace transform of the right-hand side There we have it right there. Now, because the Laplace transform is a linear transformation, you can go ahead and bring this through, and this is really going to be the Laplace transform of y double prime minus Laplace transform of y prime, etc. So I'll write that down for my next step. And then I'm going to go minus 6 times the Laplace transform of y. So if I was doing the natural log on both sides of an equation, I wouldn't be able to do this with the natural logarithm because it is not a linear transformation. But with linear transformations, we can do all those things that we dreamed about doing. On the right-hand side, I have 10 times the Laplace transform of e to the 3t. Okay, so now, if this were a face-to-face class still, I would say for the exam you would have to remember lots of Laplace transform shortcuts. But since this is a remote class, you should still try to remember them. But the Laplace transform of y double prime is s squared Laplace transform of y. Then we have minus s y of 0 minus y prime of 0. So if you're wondering what just happened, this part right here became that part right there. Okay, the next one is minus the Laplace transform of y prime. Now the Laplace transform of y prime is the slime minus yo. And, you know, sticking with colors here, we have this right here, which is that right there. Okay, and then the next one is minus 6 times the Laplace transform of y. This is going to equal 10 times the Laplace transform of e to the 3t. The Laplace transform of e to the 3t happens to be 1 over s minus 3. Okay, the other thing that I'm going to do, you know, for those of you who wanted to be very pure with the colors, there's purple, and what is this? This one right here is orange. Okay, so the thing that I want to do now is I don't want to write that again and again. So there's L of y, and there's L of y, and there's L of y, and I'm going to replace those things with w's. Okay, so I have s squared w minus, now I also want to put my initial conditions in. Y of 0 is 0, so minus 0, and then minus y prime, so minus 7. And then I'll distribute the negative, so this is minus sw. And then we have y of 0 is 0, so this is minus or plus 0, minus 6 w. This equals 10 over s minus 3. So let's go ahead and clean up the left-hand side. I have an s squared w minus sw minus 6w. And of course, we have a minus 7 here, and it doesn't have a w, so I'm going to throw it to the other side of the equation. So this equals 10 over s minus 3 plus 7. So that's what I have now. And let's continue to do this. So we have, find the annihilators. I was like looking at something, thinking of something unrelated. I'm now going to factor a w out of these three terms. So that's what I'm trying to solve for. So I have s squared minus s minus 6. This equals 10 over s minus 3 plus 7. Okay, we'll continue. Now look at this right here. So we had done this in review 4, and we did this using the annihilators, and then we did variation of parameters. But this right here, this s squared minus s minus 6, happened to correspond to the auxiliary polynomial, which was r squared minus r minus 6. So that's not a coincidence. And so we have that right there. Let's get another piece of paper. I have it right here. So I'm going to factor that. Let's see what that factors into. This is going to go w, and then we have s minus 3, and then s plus 2. And then this equals 10 over s minus 3 plus 7 plus 7. Okay, now we've talked about this in lectures, if you were looking at the lecture videos, and we talked about should we put these together or not, and it really doesn't matter. I would not put them together if I could take the inverse transform of one of these after I divide it. And if I divide by s minus 3 times s plus 2, I'm going to have an s minus 3 quantity squared times an s plus 2, which I'll need partial fractions. And then I'll have 7 over s minus 3 times s plus 2, which I would then have to do another partial fraction decomposition, and that would be 2 partial fraction decompositions? No way. So I'm going to go ahead and put those guys together by finding a common denominator of s minus 3. Now, if you want to do 2 different partial fraction decompositions, you can. Don't let me stop you. So we have the left-hand side that stays like it is, and the right-hand side I have 10 plus, and then I'll distribute that 7. 7s minus 21. This is all over s minus 3. We'll continue. So this is on the right-hand side, we have 7s minus 11, and we have s minus 3, and I'm going to write the left-hand side. Okay, so now what I'm going to do is I'm going to go ahead and divide by the s minus 3, s plus 2. So w equals 7s minus 11 all over s plus 2 times s minus 3 squared. And if we remember correctly, this w right here is really Laplace transform of y. And so what I want to do is I want to take the inverse Laplace transform on both sides of the equation, and what this would give me is y equals the inverse Laplace transform of this expression right here. So the rest of this differential equation, solving this differential equation, is finding the inverse Laplace transform. Now to do that, I'm going to use partial fractions. So do another piece of paper. So this other piece of paper here, we're going to do our partial fractions right here. 7s minus 11 all over s plus 2, s minus 3 quantity squared. This equals a over s plus 2 plus b, and we have to build up to that squared, over s minus 3 plus c over s minus 3 quantity squared. I'm going to multiply both sides of the equation by the LCD of s plus 2, s minus 3 squared, and I'm going to get 7s minus 11 equals a times s minus 3 squared plus b times s plus 2 s minus 3 plus c times s plus 2. Okay, now I'm going to go ahead and chip away at this by letting s equal certain values. I'll let s equal 3. And this is going to give me 21 minus 11 equals, why, this first guy is dead, and the second guy is dead as well. The third guy is actually going to give me the c value. Watch this. So this is c times 5. 21 minus 11 is 10. 10 equals 5c, so we know that c equals 2. Okay, now I want to put another value of s in. Maybe s equals negative 2. So this gives me negative 14 minus 11. This equals a. And then we put negative 2 in there, so we have negative 5 squared plus this guy's going to zero out, so he's dead, and then this guy is also dead. So it looks like what I have here is I have negative 25 equals 25a. So a equals negative 1, or negative 1 equals a, and that gives me the a. So now it appears that I wouldn't be able to do this trick to figure out what b is, but I still can, so watch this. S, let's see, we have our s's there, I don't know why I said s. C is 2, so I'm going to go ahead and go like this and put a 2 there. A is negative 1. And I can let my s equal whatever value I want now, and I'll do it over here. I have some room over here. S equals, let's see, how about 0? That's a good value, but it could be 27, or it could be s equals 1. You're going to get the same result. But if s is 0, I have negative 11 on the left-hand side. And then over here I have negative 1, that's the green negative 1, and then 0 is in there. That's going to be 9. Negative 3 squared is 9. Plus b. S is 0, so this is 2, this is negative 3, and then we have plus 2 times 2. So let's clean up the right-hand side. Negative 11 equals negative 9 minus 6b plus 4. Negative 11 equals negative 6b minus 5. I'm going to add 5 to both sides. I'm going to get negative 6 equals negative 6b. So that tells me that b is 1. So we are trying to do the partial fraction decomposition. Why? So we could figure out this right here, so we can figure out the inverse Laplace transform. So it looks like I have a is negative 1, b is 1, and c is 2. Now another piece of paper. I'll have this right here. So hopefully this is in the range of the camera. Yeah, it is. It's at the very top, but we'll push it down a little. Okay, so back to my solving my differential equation. I have y equals the inverse Laplace transform of, I just did the partial fraction decomposition on this, and I ended up getting -1 over s plus 2 plus 1 over s minus 3 plus 2 over s minus 3 quantity squared. Okay, so now all I have to do is find the inverse Laplace transform of those, and that's hopefully pretty straightforward. The first one's going to be, what will the first one be? Let's see, it will be negative e to the negative 2t. And then the second one's going to be plus an e to the 3t. Now the third one's going to be what? Well, there's some shifting going on here. Here's the first shifting theorem, so I'm going to temporarily ignore the -3, and it's really the inverse transform of 2 over s squared, or just 1 over s squared. The inverse transform of that is just going to be t. So this is going to be plus 2t. Now we have to account for our shift. This is the first shifting theorem, so I have e to the 3t, and this gives me exactly the same answer that I got when I used annihilators and when I used variation of parameters on this differential equation. Now you might be saying, well, I'm just going to go ahead and always use variation of parameters or annihilators, but the Laplace transform comes in very handy when this is piecewise defined, or you have a piecewise defined equation which is piecewise continuous, and you have some use of 1s and use of 2s and use of 3s, then the Laplace transform with the initial conditions is the best method. Okay, let's go ahead and do this problem again. You might be thinking, why would we want to do this problem again? For fun. No, to review. Okay, so now we're going to use vector differential equations to do this problem, and we've never really worked out a problem like this, where we converted a second order differential equation to a first order system and then solved it. But we're going to find that we're going to get the same results. Okay, so how am I going to do this? I'm going to go ahead and I'm going to say, well, that first y is going to be x1. And then y prime is going to be x2. And I'm going to go ahead and write out this system. Okay, so I have x1 prime is, well, x1 prime, so x1 is y, so x1 prime is y prime, which is going to be x2. And then x2 prime, I want to figure out what that's going to be. Well, if we rewrote this differential equation, so it said this, y double prime, but we don't want that. We'll write that as x2 prime. x2 prime minus x2 minus 6x1 equals 10e to the 3t. So if we did that, we would then be able to solve for x2 prime. To solve for x2 prime, I have 6x1 plus x2 plus 10e to the 3t. So here's the system of differential equations that I want to solve, and I'm going to use matrices to do this. Because there is a 10e to the 3t, this is a non-homogeneous system. And what it's going to look like is this. It's going to look like x prime bar, which happens to be the x1 prime and x2 prime. This equals a x bar plus vector b. Okay, well, matrix A is the coefficient matrix of the x1s and x2s on the right-hand side. So we have a 0x1 and a 1x2, and then we have a 6x1 on the bottom and a 1x2. And vector B is going to be, well, you don't have on the top equation something that is just a function of t, so I'll put a 0 there and a 10e to the 3t. So what I'm going to be doing is I'm going to be using the variation of parameters technique to do this problem. My answer is going to be this. It's going to be x bar equals the complementary solution plus the particular solution. This particular solution that's where we're going to use the variation of parameters on. So in a different color, I'll use blue. I'm going to solve this. X prime bar equals ax bar. We'll solve the associated homogeneous version of this, and then we'll know what xc is. Okay, so to do that, I have to find the eigenvalue eigenvector pairs of that matrix. So let's go ahead and write out the A minus lambda I. This equals negative lambda 1, 6, 1 minus lambda. I'll want to take the determinant of that matrix and set that thing equal to 0. When I take the determinant, I get lambda squared minus lambda minus 6. Does that remind you of anything? That should remind you of something. Remember when we had s squared minus s minus 6 when we did the Laplace transforms, and when we did review 4 and we were doing annihilators or variation of parameters on a single differential equation, that was our auxiliary polynomial. Well, when you're doing eigenvalues, this is your characteristic polynomial, which is the same thing. Look, r squared minus r minus 6. And so we should expect to see connections when we do this problem 4 different ways. I'm going to set this thing equal to 0. Hopefully we know what this thing factors into. It was lambda minus 3, lambda plus 2, so that equals 0. So I have two lambda values. Lambda equals 3 and lambda equals negative 2. Another piece of paper. So then what do I have? Well, let's go ahead and look at lambda equals 3 first. And I'm going to plug that into the A minus lambda I matrix, which is right above. And I have negative 3, 1, 6, and then 1 minus 3 is negative 2. So we can see that the rows are scalar multiples of each other. And so I'll just take the first row and I'll write it as 3, negative 1, 0, 0. And what am I trying to find? I'm trying to find the null space. Okay, so I mean, if you want, you can put an x here and a y there and say y equals t. I'm just going to zero out the first row. So my vector ends up being what? A 1, 3, or I'll write it as a column vector. 1, 3 will zero out any of those rows, really. And so I've just found eigenvalue eigenvector pairs. I should really put a t there, but I don't really need to do that for what I'm about to do. Now I'm going to look at lambda equals negative 2, and I'm going to put that into A minus lambda I and find the null space. Now, your books will say A plus 2I, and I think I've discussed this already. Maybe this is a bad habit of mine. I don't know what it is, but I like to put A minus lambda I even when I know what the lambda value is. Oh well, what are you going to do about that? You're only stuck with me for just a little bit longer, and then you don't have to watch videos or deal with me ever again. So here it goes. I put negative 2 in there. I'm putting it where? I'm putting it right there. I'm getting 2, 1, and then 6, put negative 2 in there, 3. And I can clearly see that those rows are multiples of each other, so I end up getting 2, 1, 0, 0. And what am I trying to do here? I'm trying to find the null space. And I can set y equal to t and see what x is going to be. I'm just going to figure out a vector that zeroes out that first row, and a vector that does that would be 1, negative 2. So 1, negative 2. So now I know what the complementary solution is. I'm going to go ahead and write it down, and then we'll do some variation of parameters. So the complementary solution is going to be C1 e to the 3t times the eigenvector 1, 3 plus C2 e to the negative 2t, and the eigenvector here is 1, negative 2. So that's what we have there, and this solves the part of this, okay? So this is not the whole thing. We now know what the fundamental matrix is, because this is what we're going to need on our variation of parameters. The fundamental matrix happens to be this part right here. So here, this part is the first column, and that part is the second column. So I'm going to write this as e to the 3t, 3e to the 3t. This is e to the negative 2t, negative 2, e to the negative 2t. So there's the fundamental matrix. What have I done? I have solved for xc, and now I'm solving for xp. Now xp is going to use this recipe here. The recipe being fundamental matrix times the integral of the inverse of the fundamental matrix times b dt. And what is b? b is this guy right here, which we haven't used yet. 0, 10e to the 3t. So let's see if we can do this. I have my fundamental matrix here. What I want to do first of all is I want to take the inverse, but before I take the inverse, I should probably see what the determinant is, because I'm going to go 1 over the determinant and do the shortcut for the inverse. So the determinant of the fundamental matrix is AD minus BC. So this is going to be negative 2 e to the t, and then we're going to go minus 3 e to the t, which is going to give me negative 5 e to the t. Okay, the next thing I want to do is I want to find the inverse of this matrix. I'm going to go 1 over the determinant. Oh, by the way, so some things that we've noticed. We called this right here the Wronskian, and we said it's the Wronskian of the second kind. Why? Because, you know, we are putting the vectors on the columns. Well, notice this. This guy right here is the derivative of this guy, and down here we have the derivative. So this actually is the Wronskian of the first kind as well. Now, why is that happening? Why is this happening? And the reason it's happening is because when we have our vector x bar or x prime bar, you know, you let x1 equal y and x2 equal its derivative. So that is why that is happening. That's why this is also the Wronskian of the first kind, because we are solving something that was a single differential equation that got converted to a linear system. Now, that doesn't always happen in the ones when you did in your homework. When you looked at your homework,
you didn't have the derivatives right below. So I want to point that out, that that's especially happening here because what we did. We're solving a single differential equation. Okay, so I have 1 over the determinant. I'm going to switch my DNA. And I'm going to negate my B and C. Okay, I think I'm going to need another piece of paper here. And so what am I going to do here? I'm actually going to multiply through. Maybe I'll keep the 1/5 out here. So 1/5. And I'm going to multiply through by negative 1 over e to the t. So this is going to give me, for this entry right here, a positive 2e to the negative 3t. And then this one's going to be a positive e to the negative 3t. This one's going to be a positive 3 e to the 2t, because once again, all I did was take the 1/5 and left it out there, because I didn't want to have fractions in here. And then the last one's going to be a negative e to the 2t. And so that is what we have here. And I'm trying to do this roadmap where I go x integral x inverse b. So this right here is x inverse, and what I want to do is multiply it by b. So what does b look like? That was way back here. So there's b right there. So I'm going to go ahead and multiply that right here. 0, 10 e to the 3t. That's my next step. And what is this? I'm trying to build this house here, and so the next step would go x inverse times b. So let's see what this gives us. I'm going to keep the 1/5 here. And 2 by 2 times a 2 by 1 is going to give me a 2 by 1. And so this gives me 0 plus 10. That's sweet. And then this one's going to give me a 0 minus 10 e to the 5t. Okay, so now I know what x inverse b is. What I want to do next, okay, so here's my roadmap, is I want to take the integral of that. So I want to go integral x inverse b dt. So I'm going to integrate this. When I do that, I'm going to bring the 1/5 outside the integral sign. Oh, wait a minute. Actually, this is sweet. I don't need... Wait, do I want to do that? No. I'm going to keep it outside the integral sign. And then I have 10t. And on the bottom, I'm going to do a u substitution. So I'm going to end up getting negative 2e to the 5t. So I hesitated. I was going to multiply that back through, and then I would have had fractions there. And then I ended up not having that. So this guy right here is the result. Okay, the roadmap says now I want to multiply this by the fundamental matrix X, which is pretty much out of view. Let me go ahead and write up what I'm doing. I'm going to go X integral X inverse B. Okay, so my original fundamental matrix, and you can look back, it's out of the camera range pretty much. It's e to the 3t, e to the negative 2t, 3e to the 3t, negative 2e to the negative 2t. So that's what x is. And then this part right here is what I just have. Well, I just built that one up. There's a 1/5. I'll put the 1/5 over here. And then we have this matrix right here. 10t and then negative 2e to the 5t power. Okay, so I'm going to go ahead and multiply those matrices together. That's what's going to get me my xp. So let's go ahead and do that. So xp is, okay, 1/5. Let's do some multiplication here. We have 10t e to the 3t minus 2e to the 3t. So that's the entry on the top. And then down here I'm going to get 30t e to the 3t plus 4e to the 3t. Okay, so my final answer then, and it's actually going to be a general solution so far, is I've got to go find xc. Here's xc right here, and here's xp. So let me go ahead and write the final answer down for the general solution. General solution is this guy right here, c1 e to the 3t 1, 3 plus c2 e to the negative 2t 1, negative 2 plus, do I want to bring the 1/5 in? I'll just keep the 1/5 out, but I'm also going to factor out an e to the 3t. So this is going to be e to the 3t over 5 times this vector right here, which would be 10t minus 2, 30t plus 4. And I suppose I could have factored a 2 out and wrote that as 2/5 and made that a little smaller, but that's all right. Now we are not done. Why are we not done? Because we also had this right here. We had this initial condition that says y of 0. Now remember what y is. Y is, I'll put the initial conditions in green. Y is really x1. x1 of 0 is 0. And then y prime is really x2. So this is x2 of 0 is 7. But they really could have gone like this. They could have said x bar of 0 is the vector 0, 7. Okay? So we didn't write that down when we first did this, but that is our initial condition to solve for the C1 and the C2. So let's go ahead and put that. So I know that's going to, looks like it just went away, but I'm going to write that down right here. So this is x bar of 0 is 0, 7. So it just means x bar is 0, 7 when t is 0. That's what it means. So I'm going to plug that into this equation. Let's see what we get. So this x bar is going to become 0, 7. And remember what x bar is. It really represented originally an x1 and an x2. So I'm not doing anything hopefully too strange. Then I have c1. T is 0. Good thing it is. 1, 3 plus c2 e to the 0, and then this is 1, negative 2. And then we have plus, this guy right here becomes 1/5. And then on the top we have negative 2 and 4. Let's go ahead and write down the top equation. which says 0, so I'm running along the top part of each of these vectors. 0 equals C1 plus C2 minus 2/5. And the second equation says 7 equals 3C1 minus 2C2 plus 4/5. Okay, so what I'm going to do now is I'm going to multiply these equations by 5 to get rid of that fraction. And make it bigger numbers, I guess. So I have 0 equals 5C1 plus. So now I'm just solving a system of equations. And then we have minus 2. And then this is going to be 35 equals 15C1 minus 10C2 plus 4. Another piece of paper. So let's write up the top equation a little nicer here. So the top equation is going to say 5C1 plus 5C2 equals 2. And the bottom equation says 15C1 minus 10C2 equals, that's going to be 31. Okay, I'm going to go ahead and multiply the bottom equation by, so I could be using an augmented matrix, but I'm not, by a 2. So I'll kill off the C2s. So I have 10C1 plus 10C2 equals 4. 15C1 minus 10C2 equals 3. I add those together. I end up getting 25C1 equals, almost blew it there. Almost forget to put the 1 there, so this is going to be 35. Now some of you might be looking at the answer to the problem when we did it the Laplace transform way, and you might be panicking, and that's good. Okay, so this is 35 over 25. I hope I'm doing this right. C1 equals 7 over 5. We didn't get any 7 over 5 when we did the Laplace transform, but we're not done yet, okay? I'm going to go ahead and plug this back into that equation right there. So I have 5 times C1 plus 5C2 equals 2. 7 plus 5C2 equals 2. 5C2 equals negative 5. C2 equals negative 1. Wow. So we got ourselves a C1 and a C2 value. So I'll go like this. I don't know what to do. I'm running out of space here. I know some of you are like, I could be watching Netflix, something really good, and here I am watching this lecture here. Okay, so this is, what do we have here? We have C1 equals, I just wrote on this piece of paper here. Nice. This was my guide paper. Oh well. C2 equals negative 1. So I guess I really better finish up this problem, because look, this is the paper that's taped to the desk. Some of you are like, wow, is that how he's been keeping it centered with the camera? Kind of. Okay, I don't need that anymore. I'm going to go ahead and write up this equation here. So I have x bar equals 7/5 e to the 3t 1, 3, minus e to the negative 2t. Now you're thinking, what happened? That c2 is a negative 1. Then we have this right here, 1, negative 2. And then we have plus e to the 3t over 5. That's right here. Okay, so this is a particular solution because we have the initial conditions. And let's clean this up just a little bit more here. I noticed that these guys right here can be put together, and that's what I'm going to do. So I have x bar equals, and I'll go ahead and put this guy first. So this is going to be negative e to the negative 2t, 1, negative 2. Now watch what I'm going to do here. I'm just doing some algebra. I'm going to go e to the 3t. And then what I'm going to do up here is I'm going to have, I'm going to bring that into that matrix there, into that vector. So 7/5 times 1. And on the bottom it's 7/5 times 3, so this is 21/5. What did I do that for? Okay, beautiful. Okay, now, so that's that first one. And then the second one, I'm going to bring the 1/5 in there. So I'm going to have plus 2t minus 2/5. So there's the top one, 1/5 times the top part. And 1/5 times the bottom part is going to be plus 6t plus 4/5. So let's go ahead and write it out again. This is x bar equals negative e to the negative 2t, 1, negative 2, plus e to the 3t. Look what happens here. This is nice on this problem. We have a 2t, and then 7/5 minus 2/5 is a 5/5, which is just a plus 1. And on the bottom, the same thing happens, you know, in terms of things getting pretty. We have 21 plus 4 is 25. 25 over 5 is 5. And so you might be thinking, well, what just happened here? Well, let's see what happened. This x bar, okay, so gotta try to find my, when I first, there it is. X bar is really x1, x2. So this is really x1, x2. But that x1, x2 is really, you know, when we did our substitution, and we saw that right here, we saw that x1 is y and x2 is y prime. So this is y, and this is y prime. So you can actually pick off the answer, because what was our, I keep showing you this, we were asked to solve this differential equation, weren't we? And we're trying to solve for y. They didn't ask us to solve for y prime, so I'm just going to pick off the top part. The top part actually says this. It says y equals, and so I'm following the top part right here, negative e to the negative 2t, and then I have plus 2t e to the 3t plus e to the 3t. There it is. That is the answer I got when I did the Laplace transform, and that is the answer that I got on review 4 when I did it, using annihilators and using the variation of parameters. But watch this. Look at this. The bottom one, and they didn't ask for this, it's going to be what? Negative? No, it's actually positive, because 2 negative. So this is positive 2e to the negative 2t, and then we have plus 6t e to the 3t plus 5e to the 3t. Now it doesn't look like it. It looks like it here, but this down here is the derivative of this. So if you were doing a circuit problem and you had the charge here, then we would have the current right there. And so this whole matrix development would be holding the charge and the current, because the current is the derivative. Now if you're saying, I don't see how it's the derivative, well, this one we can see, okay, because we did the chain. This one right here, we would take the derivative by going the product rule here, the derivative of the first, which is 2, times the second, e to the 3t, plus the first times the derivative of the second, which is going to give me 6t e to the 3t, and then the derivative of this was plus 3e to the 3t, and so that's where you're picking up the 5 there, and then there's the 6t. So this right here, it wasn't part of the answer. This is what we did, and we actually put our original differential equation into a first order linear system to get what we wanted.
Problem number 26 from 10.7. We have a function, f of s, here it is, and we want to find little f of t. So basically what we're doing is we are finding the inverse Laplace transform, and we notice something about this problem. We notice there is an e to some power. Now that tells us that we have to use the second shifting theorem. So let me go ahead and write out the second shifting theorem. So here's second shift, which looks like this. U sub a of t, g of t minus a, that gets transformed to e to the negative as capital G of s. And notice, we are going backwards. We're taking the inverse transform. And so that's what I have circled in blue right there. I usually circle these things in blue. And we'll have a u sub a in our problem. And our answer is going to have a u sub 3. So let's go ahead and use this as our roadmap. What we want to do is we want to identify the G of S. Well, G of S happens to be everything except this part that I have circled in blue. So G of S equals 50 over s plus 1 squared, s squared plus 4. Okay, so I have that down there. Well, the next thing I want to do is I want to find out what little g of t is. So I'm like walking back across the river. If you looked at that other lecture that we did on 10.7, I want to know what little g of t is, which means I have to take the inverse transform, or inverse Laplace transform if you'd like, of this creature right here. Well, it looks like it has lots of factors on the bottom, and what I'll be doing is everybody's favorite partial fraction decomposition. So let's decompose this expression. So what I do is I have a linear factor down here that is squared, so I'm going to take care of that by going a over s plus 1 plus b over
s plus 1 squared. That takes care of this s plus 1 quantity squared. And then I have a quadratic factor here. So I'm going to write this as plus cs plus d all over the s squared plus 4. Okay, so for the next couple of hours, I'm going to go ahead and find A, B, C, D. I'm exaggerating. It's not going to be a couple of hours, but I'm going to find those, and that's everybody's favorite part about partial fraction decomposition. Let me go ahead and put that up. We're doing a partial fraction decomposition. Okay. So what I want to do is, perhaps you see that I have an equation right here. You know, this expression equals that. I'm going to multiply that equation by the LCD. The LCD is s plus 1 squared s squared plus 4. So that's going to give me, on the left-hand side, 50 equals, okay, so when I multiply through, an s plus 1 is going to cancel, and I'll have a times s plus 1 s squared plus 4. Okay, then I multiply this expression by the LCD, and the s plus 1 squareds will cancel. And so this is going to give me b times s squared plus 4. And then this one right here is going to be, we need parentheses, cs plus d. And s squared plus 4 is going to cancel when I multiply by the LCD, so I'll just have an s plus 1 squared. Okay, so what could I do? I'm trying to find out what A, B, C, and D are. I'm going to use the chipping away method. I could let s equal -1, and that will zero out this one right here, and that term right there. So if s equals -1, I end up getting 50 equals. Okay, so -1, that expression is dead. And then we have plus b. You know, I really don't like the way this is all looking here on this piece of paper. So I'm going to go ahead and do that right there. Just kind of, okay, that looks a lot better. That was bugging me the whole time. Okay, back to this. B, and then we're putting -1 in for s. So -1 quantity squared, that's a 1 plus 4. That gives me 5. And then plus, and then we put s equals -1 right here. That's going to be 0. 50 equals 5b. B is going to equal 10 here. B is 10. Okay, so what I can do now is I can cross out that B and replace it with a 10. Now, we could try chipping away a little more, maybe letting s equal 0, but it's really not going to help anymore. So this is the case where I'm going to now multiply this all out and use the second method for partial fraction decomposition, where I set coefficients equal to coefficients. So that's what I'm going to do. So 50 equals, this is going to be fun, A times, okay, so I have to FOIL this out here. This gives me s cubed plus s squared plus 4s plus 4. So technically I didn't FOIL, I FIOL'd it, you know, because I saw that s squared there, so I did first, inside, outside, last. Who cares? I mean, if you're not sleeping by now, you know, you have this video, you're watching it on YouTube or wherever it's posted, you're pretty tough. Maybe you had a lot of caffeine. Okay, so that's what I did. I went ahead and multiplied that out. I'm just going to keep this one like this. 10s squared plus 4. And then over here, I'll multiply the s plus 1 times s plus 1. So this guy stays the same. cs plus d. And then s plus 1 times s plus 1 is going to give me an s squared plus s plus s. So that's plus 2s plus 1. Okay, so I'm continuing here. And I'm anticipating that there's going to be lots of terms here. So I'm going to go ahead and shift this over here. So I have enough room. 50 equals, I suppose I should go grab another piece of paper. I'll do that on the next step. I'm going to distribute the a in there. So this is a s cubed. And then this is plus a s squared. So yes, that's a bad word right there. So please don't call people an as squared. And then we have plus 4 as plus 4a. Okay, so we distribute the a, and now we're going to distribute the 10. So this gives me 10s squared plus 40. Well, this one's going to be fun. This is a binomial times a trinomial, so there's going to be 6 terms. I'm going to multiply through here. So why don't we go ahead and multiply cs times each of these guys. So this is going to be plus cs cubed plus 2cs squared, and then plus cs. So I went ahead so far and did that, just in case you were dozing off. And now I'm going to go ahead and multiply d times each of those. So might as well draw the arrows since I've already done it for the top one. And so we have plus ds squared plus 2ds and then plus d. So, like, good thing that I moved that 50 over here, because look at this. Woo! Okay, so that's a lot of terms. This partial fraction decomposition seems to be a bit of a pain. Could be the worst part of the problem for some of you here. Let's go ahead and get another piece of paper. What I want to do is collect some terms now. So I'm going to go ahead and use some colors. I'm going to underline all my s cubed terms in one color. So there's an s cubed. There's another one there. I don't see any other ones. Now on the left hand side of the equation, there is an s cubed, and you're like, no, you're pointing at a 50, but it's a 0s cubed. So when I go to write out this equation, I'm going to have a plus c equals 0. I'll go ahead and circle that in orange. Okay, now what I want to do is I want to do the same thing with my s squared, so I pick another color like green. So there's an s squared term. Here's an s squared term. An s squared term. And there, wow, we have 4 of them on the right hand side. On the left hand side, where the 50 is, there's a 0s squared. Just wanted to remind you about that. And what we want to do is we want to write out that equation here with the coefficients. So I have a plus 10 plus 2c plus d equals 0. Okay, 0s squared. So let's go ahead and circle that in green. Why don't we go ahead and do the same thing with just the s terms, the terms that have just an s to the 1. So we have that one right there. Okay, and then we have the cs. And this one right here. Now on the left-hand side of the equation, you have a 0s. So we'll go ahead and write that out. This is 4a plus c plus 2d equals 0. We'll circle that in blue. Okay, let's go ahead and look at our terms in this equation that are just constants. And so I just picked up orange again. I don't want to use orange, so I'll use yellow. I have a 4a and a 40. See, those do not have s's in them. And this d over here. And on the left-hand side, I have the 50, so that's going to be included. And so let's see what I'm going to write out over here. I'm going to write out 4a plus 40 plus d equals 50. We'll circle that in yellow. Okay, so what do we have here? Let's clean up these equations and just put the letters on the left and the numbers on the right. You know, see we have a 10 right there, you know, and a 40 right there. Over here, we could actually see that A and C are opposites. Another way of thinking about that is that C equals negative A. And we might not want to use that. We might want to go back up here, especially if we're going to write an augmented matrix. So on this one here, I have A, and then what do we have? Plus 2C. Oh, you know what I can do? See, I'm trying to think, do I want to put a really big augmented matrix, or do I want to replace all my C's with negative A's? And I think I want to do the second thing. So this is going to be minus 2A, okay, minus 2A. Then we have the plus D. This equals negative 10. So this one becomes, let's see, that's negative A plus D equals negative 10. Okay, so we have, that looks a lot nicer than the green. And then up here I have 4A plus C. So you know what I'm going to do? I'm going to go minus A. Now this is just one way of doing this. We could have just, you know, used matrices right away, but I like this. I feel a different mood, so why not? So we have that right there. So this gives me 3A plus 2D equals 0. Okay, so that looks more simplified than the blue one. And then over here, what do we have? We have 4A plus D, and then subtract 40 on both sides. This is going to equal 10. Okay, so let's just go like that. Now what do we have? We have A's and D's and A's and D's and A's and D's. Amazing. And we don't have B's because we solved for it with our chipping away method. So what I'm going to do is I'm going to take this equation right here and write it as A minus D equals a positive 10. So I multiply both sides by -1. And then perhaps I'll take this equation here and write it down there. Now this right here is just redundant. We should make sure all of our values work in all these equations, but I'm going to use this one right here. So this is 4A plus D equals 10. The reason I did that is I can see that my D's are going to cancel. So this gives me 5A equals 20, A equals 4. If A equals 4, then we see that C is going to equal -4. Okay. And now we just have to figure out what D is going to be. So let's figure that out. Lots of arrows here. 4 minus D equals 10. Negative D equals 6. D equals -6. I'm just going to do a visual check here. So A and C are opposites. And we have a -4 minus 6 is -10, check. And then this one right here, we should check this one. This is 12 minus 12 is 0, okay, check. And then this one right here is 16, and then -6 is 10. Okay, so this was a little sloppy. I could have probably, maybe I should have done augmented matrices, but it's done now. I'm not going to go ahead and do this again. But the deal is, we now know what these values are right here. Okay, so we said that B was 10, and so let me just circle this. Put a 10 there. Okay. A is 4. C is -4. And D is -6. What I want to do is I want to get another piece of paper so we can continue on this. So I'll pick up this paper here. So we did all this hard work of partial fraction decomposition to get this right here. So let's write out our G of S. G of S is, so we're not going to write the 50 over that junk. We're going to say 4 over S plus 1. And 10 over S plus 1 squared. And then we have minus 4s. I'm splitting this fraction here over s squared plus 4. And then we have minus 6 over s squared plus 4. And what I'm trying to do here
is I'm trying to take the Laplace transform or the inverse transform of capital F of S, and I started using the second shifting theorem. So all I'm trying to do is find little g of t, and I'm about to do that. So here it is. Little g of t is, okay, so hopefully we've remembered some of our Laplace transform formulas. I have 4 over s plus 1. That's going to give me a 4 e to the negative t. This one right here, I'm trying to take the inverse transform of that. I notice a plus 1 there. So this right here is going to be first shifting theorem. And we've made the joke, and I'm going to make it again. Sometimes when you're doing number 2, little number 1 comes out as well. Okay. And some of you are like, yeah, I'm sick of him saying that. Well, we're almost done with this semester, so you won't have to put up with me too much longer. Okay, so this is doing a little number 1 here, the first shifting theorem backwards. I ignore the plus 1, and I do the transform of 10 over s squared, the inverse transform of that, and what that will give me is 10t. Okay, I do have a 1 factorial on the top, and I'll just put the 10 out front, so this is 10t. And of course, now we have to account for the first shifting theorem. This is going to be e, and then we look at the plus 1 and we say negative t. So that takes care of the inverse transform of the first 2 terms. Now we go over here. We have an s on the top and an s squared plus 4 on the bottom. I'm going to pull the negative 4 out front. So we have negative 4, and that's going to give me the cosine. Cosine of 2t. Now this one right here doesn't have an s on the top, it has a 6. So this one's going to be the sine, and I need to have, well, there's 4 up there, so I need to have a 2 up top. So I'm going to break this 6 into 3 times 2. I'll put the 3 here, and then the 2 there. Okay, so now I'm ready to inverse transform this, energize, and this thing becomes sine 2t. So there it is. We have little g of t. So I'm going to show you the original problem here, and I'll even get rid of that. And what I'm trying to do is I'm trying to do the second shifting theorem. I found out what little g of t is, and now what I want is g of t minus something. Well, there it is right there, that minus 3. So now I'm doing the second shifting theorem. G of t minus 3. So what does that mean? That means as I'm writing this out, everywhere there is a t, I replace it with t minus 3. So for e negative, and then we have t minus 3 in parentheses, plus 10. There's a t, so t minus 3. Then e raised to the negative, and then we have t minus 3. See, I'm right here. And then I have minus 4 cosine 2 t minus 3. And then we have minus 3 sine 2 t minus 3. Okay, so I have this written out here. And now I'm ready to write out what little f of t is. I'm just going to multiply this whole thing by use of a, and a in my example is 3. So f of t equals u sub 3 of t. So I'm just looking at this right here, times g of t minus 3, so, or t minus a. I'll put a bracket here, and
wow, we have a lot of stuff here. So what I'm going to do, this is just a matter of style, is I'm going to, the good old-fashioned pencil here. I'm going to factor out an e raised to the negative quantity t minus 3. So that's what I'll do. And so what do I have left? I have a 4 plus, and then this junk right here, which is 10t minus 30. And then I have that stuff. So I'll just write it down here, minus 4 cosine 2. I suppose if you got to check the answer in the back, well, just don't check it, okay? But if you were to check the answer in the back, there's a minus. They'd probably go ahead and do the cosine subtraction formula, and you do some trig identities just to frustrate the students. Sometimes it seems like that's what they do when they write out the answer in the back. It would almost be good, except this is not simplified. So I must simplify that, okay? So let's go ahead and do that. F of t is u sub 3 t. Then we have, this is 10t minus 26. So you could, if you want it, this is stylistic, you could factor a 2 out of that. So I'm going to put the 2 out front. Though if you did write the 10t minus 26, I would not count that against you. That would be just as good. But now it's going to be 5t minus 13. And you might say, well, Joe, do you do all this crazy algebra stuff where you skip steps when you do lower algebra classes? Absolutely. It really helps out because near the end of the semester there's only like 3 people in those algebra classes, and that's a lot less grading to do. So some of you are going to be teachers. There's some tricks you can do. To thin out your classes. Woo! Okay, so there it is. That's the answer. What was the original question? It said we're supposed to find the inverse Laplace transform, and there it is. So let's go ahead and see if we can find our next problem. I think we'll do 2 more problems in this review. These problems are a little long here. So here's the next one. I went to the Chapter 9 review, and I just went ahead and picked up this problem. And this paper wants to get down. Okay, so you know what? I'll tape this down. You're going to get taped down. Well, that's going to ruin things later on. Okay, so we are to solve this system of differential equations. It doesn't look like a system, but that is the problem we're going to do. It is a system, and we put it in matrix form. So let's go ahead and do this problem. So we'll crank out this problem now. The first thing that I want to do is find A minus lambda I. Okay, A minus lambda I is going to be 10 minus lambda, negative 4, 4, and then we have 2 minus lambda. So there it is. What I want to do next is find the determinant. I'll do that right up here. The determinant of A minus lambda I. This is going to get me my eigenvalues when I set it equal to 0. This gives me, I'll do a FOIL here, so lambda squared. Then we have minus 12 lambda. And then we have plus 20. So that was AD minus BC. So minus a negative 16, that's going to be plus 16. So this gives me lambda squared minus 12 lambda plus 36. And I factor this into lambda minus 6 times lambda minus 6. So this is lambda minus 6 squared. Okay, I set this thing equal to 0, and I end up getting a lambda value of 6. It gives me algebraic multiplicity 2, because we have that 2 right there. Okay, so the next thing I want to do is we have an eigenvalue of 6. I want to find all the corresponding eigenvectors. So how do we do this? Well, I'm going to write out the A minus lambda I. With lambda equals 6. So this gives me 4, negative 4, 4. Okay, so I got the 4 by putting a 6 in there, and then I have 2 minus 6 is negative 4. Okay, so what am I trying to do with this? Well, I'm trying to find the null space. So another way of saying that is I'm trying to go A minus lambda I times V equals the 0 vector. That is what I'm trying to do. We usually don't write that when we do a lot of these problems, but that's what I'm trying to do, and that's going to help me later on when we see something in this problem. So what I do usually is I say, oh, well, let's find the null space, and I put 2 red dots there, kind of indicating that those are zeros. Okay, so we can see that this matrix reduces to 1, negative 1, 0, 0. And of course, if you're trying to find the null space, those are just zeros there. So, you know, you can say that this is x and this is y, and y equals t, and x equals t as well, and you can go through that. But what you're going to find out is you're going to find that the eigenvectors look like this. They look like t, 1, 1, where t does not equal 0. Okay, so t does not equal 0. And so these are the eigenvectors associated with the eigenvalue of 6. Now notice the geometric multiplicity is 1, okay, because there was only one parameter, t. And so we have this, this, and this would tell us that A is defective. So what am I supposed to do with this information? Well, I can write out almost the whole solution, and that's what I'm going to do. I'm going to say that the solution is this. That's what I'm trying to find, x bar. It happens to be C1 e to the 6t times an eigenvector. So the eigenvector I'm going to use is just 1, 1. I could actually use any eigenvector. I could use 7, 7. If I put a 7, 7 here, of course, yes, this C1 is there, so it's any multiple of this, just kind of like you had a t there. Okay, plus C2 And in parentheses, we put t e to the 6t 1, 1 plus, okay, so that would have been, in a perfect world, that would have been the answer, but it wasn't. And we found that out in lecture. This is going to be e raised to the 6t, and then we have a vector u there. And I was calling this the new u. The new u. Okay. So the rest of this problem involves finding out what the new u is. So it looks like I need another piece of paper here. So how do I find the new u? Oh yeah, I taped that down, didn't I? I knew I'd get me later on. To find the new u, I mean, we can do this the quick way, but I'm going to go ahead and write out another blue thing. It's going to be gotten by going like this, and we derived all this. A minus lambda I and just making sure the video's still going. A minus lambda I, here it is, u, and then this equals v. That's how you find the new u. Now there's lots of possibilities that we can put there, as we will see. So what we're going to do is we're going to do something that's similar to this. But instead of having 0, 0 there, we're going to have, so there was the 0 vector, we're going to have vector v, which we're going to say is 1, 1. Okay? So we'll move this up just a little more. So our answer is right here. We just have to figure out what that is. So a minus lambda I is 4, negative 4. 4, negative 4. And instead of putting 2 red dots there or 0, 0 there, I'm going to go ahead and put in vector v, which is 1, 1. Okay, so this gets reduced to 4, negative 4, 1, and then a whole row of zeros. And really, I didn't have to write that step, but it's good to write it. Okay, so here's x, here's y. Of course, this is bound and y is free. Okay, since y is free, we're going to say y equals t, and then the top row gives me 4x minus 4y. We're going to write 4t there. This equals 1. So what does x equal when you solve for it? X equals 4t plus 1 all over 4. Okay. So there are lots of possibilities for the new u. You could be so many different things. You have so much potential because you can let t equal whatever value you want to equal. And what I'm going to do is I will just let t equal 0. So we'll bring it back over here. T is 0, which would mean your new u is 1/4 for the x value, and for the y value it would just be 0. So we've just found the new u. We're going to write up our answer here. So let's write up the answer. It's pretty much this right here. So I have x equals c1 e to the 6t 1, 1 plus C2, and then we write out this. All I'm doing is copying this thing right here. We have T e to the 6t 1 plus e to the 6t, and then we put the u value. So the u value would be this one right here, which is 1/4 0. And by the way, this right here is the answer. Okay, so we're done with the problem, but I'm going to say a few things to finish up this problem. The first thing that I'd like to say is that this part right here, this term here, it could be written differently, and you don't have to do this. So it could be written C2, and then each of these terms inside the parentheses has an e to the 6t. So you can write it as C2 e to the 6t. And then you really can put those two vectors, you can add them together. This really says t plus 1/4. And on the bottom it says t plus 0, so that's just a t. So that's another way you could write it, you know, like if you wanted to show off to your friends. You could say, hey, I'd like to show off to my friends. And I don't know how many friends you would really have if that's kind of what you're doing. The other thing you can do, and this might help, like if you're doing an application maybe later on in a technical class and you don't like that 1/4 there. So I'll do this in purple. This is completely optional. You could multiply. I mean, remember, this is a C2. So C2 is just some constant. You can multiply this vector by whatever number you want. It could be any scalar of this. Meaning, watch this. So we can write this as C2 e to the 6t. You don't like that 1/4? Multiply this whole vector here by a 4, and you would end up getting 4t plus 1. And on the bottom you have 4t. Okay? So, I mean, this right here, I want to emphasize, you know, when you're taking the exam in this class, that this is optional. Okay, I mean, this is good enough for me right here. And so that completes problem number 5, which asks us to solve a system of differential equations. I'm going to go ahead and do one more problem that's very similar. It's from the Chapter 9 review, and we just did problem 5 from that. So the one I'm going to do now is number 10. Okay, you might say, well, Joe, it's just another problem, but this one actually will go a different direction than the last problem. It's hard to tell. It looks kind of the same. So let me just put this back up. So look at this. This is problem number 5. You know, you got this little innocent 2x2 matrix, and then you have another one. It looks like the same problem, and in some ways it is. You're solving a system of differential equations in both of them, but this one's going to have a surprise that this one did not have. And of course, there's really no surprises. If you've been doing all your homework, you'll say, oh yeah, you know, we've done problems like this. So why don't we go ahead and write out A minus lambda I. So A minus lambda I is, let's go ahead and write this down, -3 minus lambda, -10, 5, and then 11 minus lambda. Okay, so I'm going to go ahead and take the determinant just like I did in the last problem. So we have lambda minus, sorry, that's an A there. Whoops, A minus lambda I. Okay, so this gives me the characteristic equation here. We FOIL, so I have lambda squared This is the AD. I'm taking the determinant. And then we have, what do I have? I have 3 lambda minus 11 lambda. So this is going to be minus 8 lambda. And then a minus 33. And then, so that was AD minus BC. So I'm going to go minus a negative 50. That's going to give me plus 50. So this gives me lambda squared minus 8 lambda. We have plus, that gives me 17. Factors of 17 that add up to give me 8, well, it's not going to happen. So I'm going to go ahead and plug this into the quadratic formula. The quadratic formula says negative b, which is 8, plus or minus the square root of b squared, which is 64, minus 4 times a times c. So 4 times 17 times 1. So 4 times 17 is 68. This is all over 2. Okay, so what does this give me? This gives me 8 plus or minus the square root of negative 4 all over 2. This gives me 8 plus or minus 2i over 2. And that reduces to 4 plus or minus I. So in this problem, my eigenvalues happen to be imaginary numbers. So I'm going to go ahead and start off with the 4 plus I. So lambda equals 4 plus I. Each of these eigenvalues has algebraic multiplicity 1. Okay, so this has algebraic multiplicity 1, and when they all have algebraic multiplicity 1, the geometric multiplicity cannot be more than that, and so this is going to be a non-defective matrix here. So we're not going to have problems with that, but we might have problems with the imaginary numbers. Let's go ahead and write out the A minus lambda I matrix now. So I'm putting 4 plus I everywhere where lambda is. So this is going to give me a negative 7 minus I. Then I have negative 10, positive 5, and then we go 11 minus this. So this is going to give me a 7 minus I. Okay. What am I trying to find on this matrix? I'm trying to find the null space. And I'm not going to write out the A minus lambda I times V equals the 0 vector. We don't need to do that each time. I want to make the realization that both of those rows, they're scalar multiples of each other. I'm not going to verify it this time. If you've done all your work correct, that's what it will be. But you can try, multiplying one row by another row, maybe multiply the top one by 5 and the bottom one by negative 7 minus I, and you end up getting the same row for both rows. What I'm going to do is I'm going to pick one of these two rows. I'll pick the bottom row and then zero out the top row. So I'll put that bottom row on the top, 7 minus I. Then we have zeros here. So there's the matrix. We just reduced it. And here is X. Here's Y. So what do we have here? We have Y equals T. And the top row, that equation says 5x plus 7 minus I times t equals 0. So 5x equals negative 7 plus I times t, bringing that over to the right-hand side of the equation, and x equals negative 7 plus I over 5, and then t. so there it is. So I'm trying to find the eigenvectors associated with 4 plus I, that eigenvalue. And so it looks like we found them. V equals T times this right here. So I'll put the x value. So this is negative 7 plus I over 5. And then the y value is 1. Okay, so there it is. I don't like to have a fraction there. So because it's any real number times this, except we can't have 0 for t, I'm going to go ahead and just multiply both of those components by 5 and get rid of that fraction. Okay. It's a stylistic thing. You can keep the over 5 if you want. So I have t times, and then on the top we have negative 7 plus I, and then we have 5. Okay, so that's the same representation. And for stylistic purposes, what I'm going to do, and this is just me being crazy, I'm going to go 7 minus I and then a negative 5 on the bottom. Okay, but really, tomato, tomato, it doesn't matter which one you go with. And then this is t does not equal 0 because these are eigenvectors. So I've run out of paper here, and I really want to finish this problem. So what do I do next? Well, get another piece of paper. We could say, well, let's find the other eigenvectors associated with 4 minus I, okay, because that was our other eigenvalue. But we don't have to do that. Okay, so let's see what we're going to do. Our solution is going to look like this. X bar equals C1 X1 bar plus C2 X2 bar. Okay, well, the X1 bar comes from 4 plus I, and the X2 bar comes from 4 minus I. So what we can do is we can take this guy right here, so this is still a C1, and we could split that guy. So it looks like this. So it looks like X R bar plus I X I bar. And we've done this in lecture, saying, you know, and there's a theorem here, so that says you can write a general solution as C1 X R bar plus C2 X I bar. Okay, so there's a theorem that says this is just as good as this, because remember, x1 bar and x2 bar are just two vectors in a vector space, and we've taken all linear combinations, and that gives us the subspace we're looking for. Well, that subspace could have another basis, and another basis would be xr bar and xi bar, and you don't even have to mess with 4 minus I. And I'm going to color code things a little. XR bar, circle that in brown, and XI bar, we'll circle that in purple. So really all we have to do is we just have to break X1 bar into the real part plus I times the imaginary part. So that's what we're going to do. And that will finish this problem here. Hopefully it will finish it. So here it is. X1 bar equals. Okay, so we haven't even written down what it equals. It actually equals E. Okay, so let's bring this back over here. To the 4 plus I times T. So quantity 4 plus I times T. And then times the one of the eigenvectors. It could be this one right here, but I'm going to go ahead and use the one that says 7 minus I. So looks like this. 7 minus I, and then we have negative 5. Okay, and I'm going to go ahead and split this. I'm going to be doing some algebra here. Okay. So this gives me e, I'm going to use properties of exponents here, e to the 4t, and then this is e to the it, e to the it, and then over here we have 7 minus I and negative 5 on the bottom. Okay, I want to take care of this guy right here. I'm going to use the Euler formula. So I've got e to the 4t. And over here's the Euler formula, which says cosine t plus I sine t. And then this part stays the same. 7 minus I, and then we have negative 5. Okay, the next thing I'm going to do is I'm going to go ahead and multiply this guy right here into this vector. Okay. So this is e to the 4t. Now what I'm going to do here is I'm going cosine t plus I sine t times 7 minus I, so it's a binomial times a binomial. I'm going to FLOI it, FLOI it, because FL will give me the real part. So cosine t times 7 is 7 cosine t. And then here's the last part. I sine t times negative I. I'll write that out here. I sine t times negative I. So this is negative I squared sine t. I squared is negative 1, and I have negative 1 times negative 1, so this just gives me sine t. So this is plus sine t, so that was the FL, and then I will do outside, inside. So outside would be the cosine t times a negative I. So I'm going to write it a little differently. I'm going to put the I out there, and I'm going to say, well, this is just going to be negative cosine t. And then the inside is going to be 7 times I sine t. So the i's there, and I'm going to say plus 7 sine t. Now, if you wanted to take a few more steps and write it out doing a FOIL and then factoring out the I, there's nothing wrong with you. I'm going to go ahead and multiply the bottom one now. Negative 5 times this. So negative 5 cosine t. And then we have over here negative 5 I sine t. So I'm going to write it like this. I, and then over here we have negative 5 sine t. So we could rip this apart into the real part and the imaginary part. See, there's the i's right there. In fact, maybe that's what I'll do. So look at this. Maybe I won't do that. I think we could probably jump to the answer. Here's the real part right here. Times this. So I'm writing up the answer. X bar equals C1 times the brown part. So this is e to the 4t times that vector that I have in brown there. So this is 7 cosine t plus sine t. And on the bottom I have negative 5 cosine t. Plus C2
times the imaginary part, which is, it doesn't include the I. It has this part right here and this e to the 4t. So what this part is going to look like, it's going to be e to the 4t, because that's part of the purple. And then this purple part here, we're not going to put the I. Now, what happened to the I? Well, the theorem says you don't need the I, but if it makes you feel more comfortable, if it gets you better sleep at night, just, oh, I just smeared that. Just think that the I gets absorbed into the C2, if that helps you out here. So let's take care of the smear there. Okay, so this is 4t. And we have this vector here, which is the purple one. Negative cosine t plus 7 sine t. And on the bottom we have negative 5 sine t. And there it is. We have C1 times a vector plus C2 times a vector, a linear combination of two vectors, which brings us back to the linear algebra part of this class. The original question was asking us to solve this system of differential equations. Well, we have the answer right here. And so this completes the review, our last video. You're almost done with this class. Do your homework, study hard, have a good day.